A Helping Hand by Marion Creekmore. Three different scientists, William Knowles, Ryoji Nayori, and Carl Barry Sharplish, shown respectively, were awarded the Nobel Prize in 2001 for discovering catalysts that could produce specific formations of molecules. The research of this project started in the early 1960s with Knowles. Nayori and Sharplish added on to Knowles' research in 1980. Knowles is the only scientist that has died. Nayori and Sharplish both continue working in organic chemistry, where Nayori expands on his previous work and Sharplish founded click chemistry. The project focuses on the formation of specific enantiomers. Enantiomers are molecules that are mirror images that do not fit on top of each other, like your left and right hand. Although they are almost identical, they can have different properties, such as asparagine, which is sweet, and its enantiomer, which is bitter. Nature has adapted to distinguishing and producing different enantiomers. This mechanism was not understood, therefore every time a molecule was synthesized, 50% would be one way and 50% the mirror image. Because life is sensitive to chirality, or asymmetric properties, medicine needs to be a specific enantiomer. Since there was no way to select the enantiomer produced, there was a lot of waste chemicals, and efficiency was very poor. A lot of industries ended up spending lots of money to synthesize one drug. The three scientists discovered chiral enzymes that would form specific enantiomers, reducing this waste. This impacted the medical industry greatly. Knowles worked on catalyzing hydrogenation reactions, where hydrogens are added to alkenes. He modified a rhodium catalyst to contain methylpropylphenylphosphine with a 69% enantiomeric excess. This produced hydrotrophic acid and 15% enantiomer excess. Although this isn't enough to be of practical use, it was a start. On the bottom right, you can see a Hogue bomb. Inside the bomb is where the reaction took place. It has a pressure gauge and a thermocouple attached to it. Knowles discovered that a rhodium complex containing DPAMP that catalyzes a hydrogenation reaction resulted in a 95% enantiomeric excess of amino acid B. Amino acid B is used to synthesize the amino acid L-dopa, which is used to treat Parkinson's. This reaction is still used today. For this work, Knowles received 1/4 of the Nobel Prize. In 1980, Nayori discovered BINAP. This molecule has two enantiomers that can be bounded to rubidium or rhodium to create an effective catalyst for asymmetric hydrogenation of many different molecules, including ketones, esters, and carboxylic acids. This catalyst is used in industries to create pharmaceuticals, agrochemicals, flavors, and fragrances. This molecule is more efficient than Knowles' catalyst with a decreased cost, simpler reaction, and higher enantiomeric excess. This work earned Nayori 1/4 of the Nobel Prize. Sharplish worked to find catalysts to aid in oxidation reactions rather than hydrogenation. He discovered that an enantiomerically pure titanium tartrate complex could epoxidize allylic alcohols with control over the enantiomer produced, with a 70 to 90% enantiomeric excess. This reaction is more efficient with the use of a molecular sieve, as shown on the right. When the D-tartrate ligand is used, the oxygen is added to the top of the alkene. When the L-tartrate ligand is used, the oxygen is added to the bottom of the alkene. These reactions provided a more efficient way to produce molecules needed for drug synthesis, and also were able to produce gypsy moth pheromone traps. A round bottom flash was used for this reaction, which is shown in the top right-hand corner. This work led to Sharplish getting 1/2 of the Nobel Prize credit. In conclusion, these three scientists found a more economically feasible way to produce chemicals needed for drug synthesization and insecticides. These scientists led a revolution in chemistry that is continued today as more compatible ligands are found that produce higher efficiency.